Test. All right, good evening. Let's get started. So we've done double integral, we've done applications double integral. So now let's move on to triple integrals. Okay, so first, let's take a look at how triple integral is derived, okay, through an application of this triple integral. Okay, suppose that we have a region D. Which is basically a bounded region in 3D space. Oh, I'm not sharing. Not sharing. All right. Okay, here we go. Okay, suppose we have a region D. It's a bounded region in 3D space. So by that, okay, we mean something like this. So you can draw an arbitrary region D. So this is the region D we're talking about here. It's bounded, it's not open, right? No. It's either a cube or a sphere, but it's even a cylinder, right? But it has to be a bounded region. And at the same time, okay, you have a region D. At the same time, also consider a given function, let's call it W. And this time, this W is a function of 3 variables. So W equal to f of x, y, z. And then this function, okay, is defined over region D. So those are the given conditions at here. Okay, so again, I want to emphasize, what does it mean by the functions defined over the region D? Okay. So this is a function of 3 variables, and the reason because region D is a 3D region. So if you pick any point in the 3D region, then that point has a coordinate x, y, z, and you plug it into this function, then the function will give you back a value. Right? So that's basically what it means, this function defined over the region D. If somehow the function gives you back infinite, then that's not what we call defined over the region D. Okay. So objective at here is to calculate the integral of this function over region D. Very much like single function. You integrate this function from A to B. Double integral, you integrate the function 2 variable over a thin plate or region R. Right? So now we're trying to figure out what does it mean by integrate this function f of x, y over this given 3D region D. Okay. So let's start with a physical formulation kind of problem, and then we'll see how they end up with. Okay. All right, so let's assume this function, give this function a meaning. Let's assume this is a density. So assume that it as density function. So now my question here is to change this objective to a slightly different question. Then what is the mass of a solid given by region D? So your region D here is already a 3D region. Assuming this 3D region actually represents a 3D object. And then the 3D object has a density f of x, y, z. Then what is the total mass, right, of this 3D object? So that's a same, it's different, it's a physical meaning type of question, but the objective, as you will see, is exactly the same objective to be achieved. So let's calculate the mass. So here's what we're going to do. Let's pick a point within this region D, and then we can create a very small cube around that location. So you pick a point and create a very, very small cube around that location. So let's see. So let's say suppose this is a location at xi, yi, zi. Then we create a small region with a delta x, delta y, and delta z, right, for that little cube. So now I'm going to calculate the mass of the little cube. Okay. So assuming basically it's small, so then we can assume that the density, right, within that little cube is even, is constant. Then mass is basically the volume of the cube times the density of the cube. Okay. So volume times this, then you got the mass. Volume basically is what? Delta x, delta y, delta z. All right, so now you got the small mass for the cube. Then you can see, okay, then the total mass can be approximated as a summation of all of the masses of the small cube. So you sum, there's a number of them up, then you get an approximated mass for this huge object represented by the region D. And then we let this n go to infinite, right? So sigma will become integral, and we'll see it become a triple integral basically, right? And then the delta will become d, right? Differential. So this formula in here will become mass, okay, equal. Go back to this delta m and here, okay, become the density times dx, dy, dz. Okay, then you're integrating, right? But look at that, we have dx, dy, dz. So basically, you're going to have 3 different integrations. Integrate over the given region D. So that's what we call a triple integral. And this is basically you integrate a function f over the region D, right? That's basically the objective, to calculate the integral of this function over the region D. And the integral involves 3 different separate integrations, right? So this is called a triple integral. Okay, so now the question basically, right, is to boils down to how to calculate this triple integral. Now, if you recall in double integral, we talked about calculating double integral using Cartesian coordinates, using polar coordinates, right? So for triple integral, which basically you're doing in 3D space, we will have a very similar approaches. The first approach is to be in Cartesian coordinates. And the second approach is not going to be polar, is what we call cylindrical coordinates. And third one is called spherical coordinates. So we have 3 different coordinate systems we can make use of to calculate this triple integral. First, let's look at the Cartesian coordinates. No matter what coordinates you're going to use, okay, when you calculate a triple integral at here, it's always about how you integrate over this region D, and it's all about how you can find the limit for the variables or the coordinates variables, and in this case, dx, dy, dz, but you can always change the order, right? So that's what we're going to do here. So let's look at how we can find the integral limits. Okay. The key here, okay, the key is to scan through region D. Okay. Remember, I also had a similar wording for double integral to scan through region R. Yes. Got a question? Oh, no, okay. So the key is to scan through this region R, but without redundancy here, okay? So here's the steps. Step one. Step one is to decide on the order of integration. Order integration basically means here's your dx, dy, dz. Okay, so technically this is basically your dv, the volume, delta v become dv. So dv can be dx, dy, dz, and it can be dx, dz, dy, or it can be dy, dz, dx, right? Continue. There are 9 combinations basically. Okay. So which order do you choose? It's up to you, right? So technically, usually it doesn't really matter, but of course, sometimes the order doesn't matter, right? So I'm not going to be too picky for now. And so let's just try, okay, for example, let's try dz and then dy dx. So often in time, you wanted to try this order as so try the z first. You'll see why. Okay, yeah. So dz first, and then dy dx. Okay. So second step is now you decided on order now, and then right. The second step is you need to sketch the region D. Okay. So whatever the questions given to you. Okay, so question probably tells you region D consists of a surface and a plane, you know, and then you draw the surface out, draw the plane, right? Together, they will form a region D, right? So that's what we mean by sketch it out, because without a sketch, right, it's very hard to imagine. Okay? Now, not only you sketch this region D out, you also want to sketch, okay, sketch the shadow of D in XY plane. So you might wonder why you sketch the shadow of the D in XY plane. This is determined by the first step. So recalling that here, we're going to try dz, dy, dx, right? So basically means you're going to try to find the z limit and then find y and x limit. So the y and x limit, which basically is the reason why you want to sketch the shadow of the D in XY plane, because the shadow will give me the Y and X limit. Shadow basically means you're projecting D, okay, into XY plane. So projecting, you just look it down, right? It's like a top view. Okay? You look at it down, and what does this region D look like? And that view, right, give you this shadow. So whenever you decide on the order, right, if the next time you decide to order, let's say dx, dy, dz, okay, then guess what? Then you need to sketch the shadow in the yz plane. Okay, that's based on your choice of the order of the integration. Okay. And once you've done this, try to label all boundaries. For both of the D and the shadow. So let's call the shadow as R. Okay, so sketch the shadow R of the D in XY plane. D is a 3D region, R is a 2D region, very much like the double integral. Okay, then the third step is to find the Z limit. Because the Z is our first order of business, right? So we have to find the Z limits first. Okay, so I'm gonna draw a fictitious of a region D at here, okay? So, and then to illustrate how we scan through the region D, how we find the limits for the Z, the Y, and the X. So let's suppose that I have a region D which looks like this. Okay. So it's like a cylindrical type of objects. Okay, there's top surface, there's a bottom surface, and then there's side bodies. Okay. So first step, as we said, you need to sketch this, okay, sketch that, and label it. So let's say the top surface is Z2 equal to F2. I just call it Z. Z2 equal to F2 of XY. And then the bottom surface is Z equal to F1 of XY. Okay. So this is the 3D region. This is your region D. Okay. And once you get this, and then we project this region D onto XY plane. Okay. So projecting it onto XY plane, now assuming that the end results of the projection, okay, give me a region R, looks like this one. And then this region, depending on the actual region D you sketch, you'll get some kind of a shadow, right? So suppose for this shadow, it has two boundaries. This boundary, let's call this is Y equal to G2 of X. And this boundary, let's call this Y equal to G1 of X. So those are the results of the second step, doing all the proper sketch and a proper labeling of the boundaries. Okay, so now let's do the third step, is how do we scan through this region D? Okay, here's a proper step. First, you draw an arrow line. Let's call it M, through a point in the shadow, and in the positive Z-axis direction. So that's step number one, scan. So you're essentially scan this, let's call this scan step one. So let's do it. Let's see what do we mean by doing this step here. First, you draw an arrow line through a point in the shadow. So you pick a point in the shadow. Then you draw the arrow line in the positive Z-axis direction. Okay. Because of this, you pick the point in the shadow. So when you draw it in the positive Z-axis direction, then it's guaranteed that this arrow line will pass through this region D. Okay. Then apparently you will have an intersection, right? Intersection between this arrow line and the bottom surface. You will have intersection of this arrow line of the top surface. So the first scan is like you created, okay, from the bottom to the top. This scan here, you created a straight line, a line segment. Remember the idea to scan through the region D. Okay, so it's not quite done yet. The first step only creating or generating this green line segment. Then first contact, very much like what we done before. So first contact give you the Z mean. And because the Z mean or the first contact is at the bottom surface, which is this surface here. So Z mean will be represented by the surface function F1. And second contact will give you the Z max. So that is represented by the top surface F of XY, F2 of XY. Right, so that basically give you is what's the height, right, from the contact point to the XY plane. And what's the height from the contact point to the XY plane, which is the two function values. So that give you the Z limits. Okay, so then this is what we're going to plug in for the triple integral. Right. Okay, good. This is the first step of a scan. And then find the Y limits. So this will be the scan step number 2. So for this step, how you scan is you can draw an arrow line. Let's call this N in the positive Y-axis direction. So next time you're scanning in the Y-axis direction. So here's what's happening here. Suppose this is the initial point, so you draw an arrow line. Okay, this is N here in the positive Y-axis direction, so parallel. Okay. So what really is going on here is, remember you're trying to scan through, right? So this line segment that you have generated based from the first step of scan, you're essentially is moving from one end to another end. You're trying to scan through in the Y-axis direction. And while you're doing this, so then what happens is you're literally just generating a cross section, right? Cross section in here. You're literally just generating cross section based on this step number 2 scan. Okay. So you draw the arrow line across the shadow here. Okay, remember this one here, you draw it. You draw an arrow line here and then Y-axis cross the shadow. Across the shadow R. So you will have a first contact point. The first contact with R will give you the Y mean. And the second contact with R will give you the Y max as you roll. So assuming the first contact falls onto this curve, the boundary G1x, then your Y mean is G1 of X. And if it falls on the second one, falls on the G2, your Y mean will be G2 of X. Okay. Now you get the limits for the Y variable and based on the scan step number 2. The final step of scan is to find X limits. And also this step of scan is supposed to finish the scanning task of the region D. Okay. So for this last step, you move, okay, you move the arrow line, right? The arrow line N based on this scan step number 2. You move this arrow line in the X-axis direction. Okay. So when you're moving this, you're trying to find the edges. Okay. Find the edges that sandwich. Okay, the sandwich is this region R or the shadow. try to find this edge that bound this shadow. So you will have two edges. One edge give you X mean, and the other edge will give you X max. Okay? And these two edges, which is the last step scan, has to be constants, not going to be any variables, right? Otherwise, you won't get a number, right, from your triple integral. Okay, so what happens is the last step is you scan it, right? You scan and you scan. So you have A here, you have a B here. So that gives you a minimum and a maximum value for the X limits. And also in your head, you can think about what's going on with the scan is, so this last step scan. Remember the second step created this cross section, right? So last step is you're moving the cross section from this end to the other end. As you're moving, you're literally basically generating this 3D region D, right? So that's what we call scanning through this region D. Okay, it's like a 3D printing process. Okay, so you print the line, and you keep printing. Then you get a cross section, and then you print the cross section up. Then you got the whole region D, right? Yeah. Okay, so that's the process for finding the Cartesian coordinates limits. So finally, you can put all of the informations into the triple integral. So we're integrating at order of dz, dy, dx. So the first limits give me y1, f1 of xy, f2 of xy. The second one give me g1 of x, g2 of x give me a to b. Okay. And the rest of the work is just be carefully calculate integrals in and out. And when you calculate the first integral with respect to z, you're going to treat the x and y as constants. And then once you get the first step done, then the z will be gone. You integrate with respect to y, but you treat x as constant. Right? So that way, at the end of the day, you will get a number, right, for this triple integral. Okay, so let's see take a look at a simple example here. Okay, look at a simpler region D. All right, so this is a surface. This is a plane. Here's a plane, x plus y plus z equal to 1. So what we call the region D here. Okay. Region D is the space between, let's call this is the space between x plus y plus z equal to 1 and x, y, z, and x, y, y, z, and z, x planes. Okay, so that's the region D, how D is defined. You know, sometimes if the question doesn't sketch it for you, right, just give you a description like that, then you have to be able to sketch that. Essentially, the region D is the corner, right? It's the corner in here, but of course, with the plane on top of it. Okay, that's your region D. And I want to find the volume of this region D. Okay. Try to find the volume of the region. This is very much like an application, right? So technically, you don't really need a triple integral, and even high school student probably will be able to get a volume, right? The volume in here this is called a tetrahedron. You could just calculate the bottom of the area times the height and then divide it by 3, right? So you get a volume. But let's try triple integral. Okay? So recall that the triple integral formula triple integral formula is this. Okay? So I'm going to let Right? How am I going to get formula for 3.4 volume? So I'm going to let this function equal to 1. So the integrand, this is the integrand here, right? You're letting integrand equal to 1. Then this triple integral become, right? Become this. So basically you're integrating, the integrand here is 1, and you won't have a dv at here. And again, this falls into, when you integrate d anything, you get back to whatever in the bracket. So now you're integrating d, which is the v, so, right? So you should get volume. So this integral should give you the volume of this region d. Okay, so that's what we're going to use for this integral at here. And all I need to do is, right, dv is dz, dx, dy, or whatever the combination, multiplication of the combination of 3 variables. So choose the order, right? So let's just choose dz, dy, dx as we have done in that generic question. Can you choose another orders? Absolutely, okay, absolutely you can. So actually I want you to try a different order, see if it makes any difference. Should it switch? So you got a 1 here, Chris, okay? So now the question basically to find the limits for z, the limit for y, and the limit for the x. So let's go back to this, to the sketch here. Remember the step number 2 is sketch the region D and also sketch the shadow as long as you have decided on the order. Now, because our order here is dz, dy, dx, so the shadow would be the shadow in the xy plane. So the current structure or geometry, when you project it into the xy plane, that seems to be very straightforward. So you get this triangle here. So that's the shadow of this region D in xy plane. So you call this is region D, and this shadow here will be your region R, right? Yeah. And Z limits, according to the procedure, you pick a point, okay, inside this shadow R, then you draw an arrow line, okay, in the direction of Z-axis. Okay. And apparently you will have a first contact point right in the XY plane, and then second contact point, which will be on the plane. So your Z mean will be 0, and your Z max will be decided by the top surface, which is this. So Z max is 1 minus X minus Y, right? That's based on your plane giving it here. So now we got the Z limit for this question. Okay, next step, the XY limits is purely, right, can be purely determined by the shadow or the region R. Right, as we have done in the generic example, you draw an arrow line in the y-axis direction. First step, first contact, Y mean. Second contact, Y max. So first contact 0, and second contact is this line here. So now the question is, okay, so then what is this line, right? So you need an expression for this line to give you the Y max. So can anybody actually tell me what would be this line equation? And this line is the intersection, yes. That's right? Very simple, because this line is the intersection between the plane and the XY plane. The XY plane basically means the Z equal to 0. So you just have to set X equal to 0, and you got a line X plus Y equal to 1. Okay, so that line here is X plus Y equal to 1. Then the Y limit is 1 minus X. Final step, to sweep this arrow line from one end to another end, or one edge to another edge. So that gives you 0 to this location. Okay, that location can be easily obtained based on this line equation, which is 1. So this is the setup for this triple integral. Okay. And then the rest of the work, okay, is to calculate this triple integral, right, in and out. And I think it is a very simple street integral here. There's no trick at all. Okay, so you're going to get 1/6. Okay. So you can verify, right? You know, you can see, does that give you 1/6 if you use the formula from the high school? Yeah, so there's 1, 1, 1/2 times 1 times 1/3, you get 1/6, right? Yeah. Okay, so triple integral over Cartesian coordinates. As you can see, there's quite a bit of a similarity as double integrals, right? You just added 1, you know, that's added the z limits. But the procedure, the principle in the back is exactly the same. You try to scan through this region. So I want you to try, you should try different orders. Can you try, say, for example, dx, dy, dz? If you try this order, okay, what will be the integral limits? What will be basically, for example, if you try dx, dy, dz, then what will be the shadow, right? First step. So the shadow will be in the YZ plane. So will be that triangle over there, right? Yeah. The limits will be different. The results will be the same. So try it. You can try different orders. Okay, any questions on this Cartesian coordinates? I think if you're familiar with the double integral, if you're familiar with the concept of scan through, this is shouldn't be too difficult. Okay. So now let's take a look at triple integral in cylindrical coordinates. Okay, this is different. This is first time hearing it, but you will see that it has a lot to do the polar coordinates. So this is a new coordinate system. It's called cylindrical coordinates. And this is a cylindrical coordinates, basically like in 3D space, like Cartesian, right? It's a different way to describe the location of a point. Okay, let's say this is our X, Y, Z coordinate system. And here's a point P with a coordinates of X, Y, Z. So X, Y, Z, it means you drop it down over here and then you project it, right? So this is your X, this is your Y, and this is your Z, and that's the coordinates of this point P. So as long as you give X, Y, Z, then people know exactly where to find this point P. Right? So alternatively, I can find another 3 variables to describe this location. So this alternative solution is using R, okay? So you find this distance, okay, to this location, R, and then you use theta. So you look at R and theta, what does that remind you? It's the same as the polar coordinates, right? Yeah. And then you're not changing, you still use the Z. So this time, so we use R, theta, Z. We use these 3 variables to describe the Z, the point P location, okay? So this is basically R, theta, Z versus this X, Y, Z. Cartesian, cylindrical. Okay. This is cylindrical, this is Cartesian. Now, apparently, you can write down the relationship. Right? So X is equal to R cosine theta, and Y equal to R sine theta. And these 2 together, that's essentially your polar coordinates. Right? And now Z, you're not changing it. Z is still the same as Z. So the relationship between Cartesian and cylindrical essentially is this. And sometimes if it helps, you can think of this. So at this location P, at the P point, you have basically you can draw a small coordinate system in the direction of R. Okay, so this is the reading direction. You can establish a unit vector. So this unit vector is like the I hat, right, in the x-axis direction. But this one is in the R direction. And then another one is perpendicular to the ER, but pointing to the direction of rotation by theta angle. So another unit vector in the theta direction. And finally, you have a direction unit vector in the Z direction. So the three together is like a basically a T and B frame, right? So tangent, normal, and binormal. So T and B. So cross product satisfies cross product rule, right hand rule. So this is the so-called cylindrical coordinates, right, associated with that point P. So if a point P move to a different location, then that coordinate is supposed to also associated coordinates also move to a different location. Okay. So the point here is we're not going to evaluate the triple integral using x, y, z anymore. We want to integrate. The triple integral, okay, using the cylindrical coordinate stuff. So this is essentially the same idea as the so-called change of variables. So you're changing variable from x, y, z to r theta z. So technically, I can quickly use the Jacobian, the change of variable formula to give us a new formula here. When you change from x, y, z to r theta z, okay, the region D, okay, could possibly transform to a different shape. But in this case, usually they don't, okay? Especially just like from XY to polar, or from, in this case, from XYZ Cartesian to cylindrical, the region D will be kept exactly the same shape. Okay, so even though we call it D prime. So what we do is we're going to replace the X with R cosine theta, replace the Y with R sine, and Z, we're going to keep it as it is, okay, as Z. Then instead of doing dx, dy, dz, so we will do, okay, dz, dr, d theta. Okay. However, as you recall, okay, over here, there needs to be a scaling factor. And this scaling factor is given by the determinant of the Jacobian, absolute value of that. Okay. So now let's take a look at how do we get that Jacobian matrix, and then how do we get the determinant of the Jacobian. Okay. So Jacobian matrix first. Jacobian matrix, here is your x, y, z. This is the relationship between r, x, y, z, and r theta. So x is a function of x is a function of r theta z, except z is not really there. Y is also a function of r theta z, and z is a function of r theta z, right? So this is in the format of the generic vector coordinate transformation. So Jacobian, construct Jacobian partial x over partial r, partial x, partial theta, partial x, partial z. That's your first row. Partial y, partial r, partial y, partial theta, partial y, partial z. And the next one, last one, same thing. There. So that is your Jacobian matrix. Okay, so then you calculate each one of the term. It's not very difficult to calculate. So calculate each one of the partial derivative. Cosine theta is the first one, negative r sine theta. X has no z in it, so partial x over partial z, that'll be 0. And then partial y over partial r sine theta. And then here is r cosine theta. Again, last term 0. And the last one, partial z or partial r, turns to 0, 0. Partial z or partial z, sorry, this one is z. Partial z or partial z, okay, this is 1, right? Yeah, there's only one z. Okay. So this is your Jacobian matrix. And we're looking for is the determinant of the Jacobian. So when you calculate determinant of this 3 by 3, it's because this is 0, 0, 1, this is also 0, 0, 1 here. So you're actually calculating is the determinant of this 2 by 2 times 1. And that give you r. Okay. It's the same results at the polar coordinates, right? Yeah. So all you need to do is replace the question mark with the r at here. So your new triple integral, okay, is r, okay, dz, dr, d theta. Okay. So you notice that I have purposely written the dz as the first of the order, and then dr, d theta, right? Yeah. So the reason is basically I'm trying to remind you that the order at here, best order for cylindrical is to do the dz first, and then dr, d theta. Okay. So when you do the dz, okay, we'll see that, and that's fine, which is basically the same procedure as you find the z limits for like a Cartesian coordinates. And when you try the limits for the r theta, you look at r theta, okay, from the shadow, right? The shadow which is in the xy plane. So very much like a Cartesian, the order very much like a Cartesian, except the first step is same. The next two steps, instead of xy, now you're looking at is r and theta limits. Okay. So this order, okay, definitely works in favor of you. But does that mean that the other order doesn't work? Yes, it does. Okay, so but just so sometimes it's not as straightforward as you do this order. Okay, yeah. So let's look at an example here, how we can properly find. Do I have a time? A couple minutes. Okay, it's not much time. Anyway, so well, let's start example, then we can continue. Okay. Region D is given by these two surfaces. And we want to calculate the volume bounded by these two surfaces. So first step, sketch the two surfaces. I think by this time, you should be very comfortable. When you look at the first one, and you know exactly, okay, this gives me a parabola which pointing up. And the second one, this should give me a parabola pointing down. Because the 4 right here, so the top of the parabola is at a z equal to 4, right? So you can draw a parabola pointing down, okay, and here's 4. So then you can see the two surfaces, right? It's like two bows on top of each other. And the region D is the area or the region between the two surfaces. Okay, that's the region D, and that's the volume we're trying to find it out from. Okay. Now, you can certainly actually use Cartesian coordinates. Okay, so you can try actually in Cartesian. If I try Cartesian coordinates, let's say I use dz, dy, dx. Okay, if this is the order. But before we look at this, the limits here, remember the steps. If I decided to use dz first, then I need to find the shadow of this region D. So if you project this region D onto XY plane, now you're supposed to get a geometry like this. It's a circle, but why is it going to be a circle? So you have to look at these two together, right, to decide on this projected shadow. So if you look at the two surfaces given it here, okay, apparently the two surfaces will intersect. When they intersect, the Z value will be the same. So that means for this part of the intersection here, now you got x squared plus y squared equal to 4 minus x squared minus y squared. Right, that's the place intersection. And you simplify this, you get x squared plus y squared equal to 2. And that is a circle. So this shadow here, right, is the circle there. Okay, that's the projected circle. And we'll use this circle, right, for whatever reason, for whatever purpose we can do. So I'm going to stop here, and we can look at the difference between Cartesian coordinates and cylindrical coordinates. Okay, and you will see the cylindrical coordinates actually much easier to compute the result. Okay. Not necessarily in terms of finding the limits for the integral. Okay. All right. So anyway, we have a break ahead of us. So I believe some of you have some catch up to do, but otherwise, really make use of the break. Take a good break, and when you come back, there should be a little more energy showing from you. Yeah. Okay. Absolutely.